research under supervision of Professor Miguel Valero and co-supervision of Dr. Mahan Motamedi, collaboration with Navier Laboratory from École de Pontcarré, and under application of the GSA laboratory at the Malachy School of Architecture. The structure of this presentation today is divided by 5 sections. The first part is about introduction and research background. The second part is about design strategies. Third part is about material considerations. And fourth, about fabrication methods. And last is conclusion and future goals. Introduction and research background. In order to define the area of this research, I have to say that additive manufacturing of cantilever earthen structures is a multidisciplinary field comprising 9 different fields. Computational design, computer graphics, geotechnical engineering, material science, civil engineering, traditional masonry, life cycle analysis, robotic and automation, topological design. And my research stands somewhere in the highlighted red area, meaning that I have a high contribution to the robotic automation, computational design, and traditional masonry, and medium level of contribution to geotechnical engineering, material science, topological design. The problem statement of this research is the false work. False work is a false plus work, meaning that it's an undesirable aspect of construction which should be eliminated. Formwork can account for approximately 35 to 40% of total cost of concrete construction. Labor costs associated with the formwork can be significant, especially in the countries that the labor costs are higher than the others. And formwork can contribute to the construction of the construction waste and consumption of the natural resources. The contemporary shows, in terms of the construction process, they are wasteful. The first example is a low monothesis shell by Felix Candela. As you can see, the shell is designed in a way that the formworks can be reusable. However, the number of the labor need to install these formworks is intensive, and today it's not affordable anymore. The second example is the Rolex Learning Center. However, the design of this structure is done by advanced tools. The construction still remains conventional, and for the construction, they need massive amount of formwork, which will be disposed after the construction. The third example is the Stratus concrete 3D printed masonry bridge done by Philippe Bloch Research Group. However, the construction method and the design method are both advanced, and the blocks are printed without any scaffolding. The assembly of the modules needs a massive amount of formworks, which makes the construction process remains wasteful. However, ancient molding techniques, especially in arid areas, the muscles were used to fabricate bolts without any formwork, using special techniques of bricklaying. The first example is the ancient domes. On the left, you can see the Sultanian dome or Oljaito, with inner circle diameter of 25 meters. And 100 years after, there's the dome of the Santa Maria del Fiore, which is a double-layered dome with the inner circle diameter of 45 meters. To the best of my knowledge, this is the largest dome ever made without any formwork. And now we have an example of a vault. As you can see here is the Tisfon Palace vault made for the Persian king in Sassanid era, with the depth of 52 meters, span of 26 meters, and the height of 30 meters, which was fabricated with no formwork. And this is the largest ever vault made ever by him. The methodology of this research is to make a transition from the brick layers to the print layers and have inspiration from the techniques of the ancient masons and imitate their technique in order to print bolts without any scaffolding. The objective of this research is to reduce construction embodied energy, reducing the overuse of natural resources, reduction of the construction waste, labor cost, the material cost, and increase the construction quality and speed. The solution offered by the Scaffold-Free 3D Printing of Earthen Shells is using locally excavated low-impact material, eliminating the use of formwork in the construction process and automation in construction. There are several available 3D printing setups in the market. Robotic arms, robotic on track, mobile robots, crane, gantry crane, multi-crane, cable-driven, and swarm drones. In our research, we will use a robotic arm on the track and fixed robotic arms. The advantage of using the robotic arm is the ability to print the layers of the cantilever structure projected together. Here in the section, as you can see, the image on the left shows that the normal conventional printing, which is based on XYZ movement. And as you can see, the local cantilevers in between the layers. However, using the 3D 6-axis robots, we can have the printing, as you can see at the right, in which the layers are completely perpendicular, projected together in a perpendicular way, eliminating the occurrence of the local bending moments. Using any of these 3D printing setups, we can have 5 different printing regimes. Printing regimes is the method that we deposit the material. So the first one is the infinite print extrusion, in which the material will exit the nozzle in an unsheared state, meaning that it is stiff enough in order to not deform under its shape, and it it holds its shape, and it keeps the shape of the nozzle. The second one is the slip forming. In terms of material condition, it's the same as infinite brick extrusion. However, the layer is printed vertically and using a dynamic shape nozzles. The third one is the free deposition, in which we have no control over the geometry of the layer, and the geometry of the layer is governed by the thixotropy of the material and the gravity. The fourth one is the layer pressing. In this printing regime, the height of the layer is governed by the height of the nozzle from the printing bed, and also we can control the shape of the layer by using the nozzle. So for example, in the oriented layer pressing, we can control the shape of the lateral part of the layer. And in this research, we are going to use layer pressing and oriented layer pressing printing regimes. So as a conclusion for the introduction, first we introduce the literature review and problem statement and our methodology. And then we introduce the 3 available 3D printing setup and advantage of using the 6-axis robot. And then we introduce the 5 different 3D printing regimes. So the second chapter is about the strategies, design strategies. The material of this chapter is already published in 3 different articles. So here is the graph that shows the contribution of this chapter to the field. So in this chapter, we have a high contribution to the computational design and robotic automation and traditional masonry. So the outline of this chapter is the same as here. Ancient molding techniques with no formworks. First, we are going to show some examples. And then we introduce the patching design grammar. The additive manufacturing of earth-based materials was introduced in 2012 by 3 groups at the same time. First was the Building Bytes by Brian Peters. Second was FabLab by IAC, and third was by RASP company. The people who are working on this topic, the first one was Paul Carnot. He had worked on printing cantilever structure by concrete, and he has developed a form-finding fabrication level form-finding tool to develop this method. The second example is the contest, NASA's Habitat Contest, and the proposal of the Penn State Research Group, led by Professor Joseph Pinto-Duarte and Shadi Hazarian. And this shell was also printed by concrete without any formwork. The third one is the multi-objective optimization method for 3D printing earth and concrete shells, doing by Alexandre Kerr. Another example is Casa Covida, done by Ronald Ryle. So as you can see here, 3 dome-like shells are printed using the simple gantry. And the next example is the circular shell, circular dome-like shell done by Was and Mario Cucinella. And the last example is again attributed to the Ronald Rao, in which a shell with a rectangular base is fully printed without any scaffolding using a mobile robot. So the problem statement of this chapter is that all the examples that we show, they are restricted to the circular and rectangular boundary, and the dimension of these shells are restricted by the material constraint and also the fabrication setup. Our question is that possible to divide these boundaries into the sub-boundaries and cover the spans of the sub-boundaries using a self-supporting interconnected elements? And if the answer is yes, can we extend these simple boundaries into the more complex boundaries? Our methodology is to identify the bolts that use no formwork and decode those bolts based on their support condition and the boundary configuration, and manipulate those supports and topology of those bolts in order to create a new type of bolts that never existed before. Here I'm going to present different types of bolting techniques that use no formwork. The first one is the squinch bolt. And as you can see at the left, this is a support configuration of the squinch bolt. The second one is a barrel or pitch bolt, in which the first layer of the bolt is always supported by a straight bolt. And here is the support configuration. The third one is the ground supported bolt. So the first layer of this bolt is always supported by the ground instead of a straight bolt. And the topology is the same as here. And the last one is the dome. Dome are type of the bolts which are constructed on a periodic or closed boundary, such as this one. Now I want to introduce the patching design grammar. The patching method is inspired by ancient bolting techniques without formwork, especially the squinch bolt technique, which is originally called field push in Persian bolting vocabulary. Field push is a method to convert quad boundaries, such as the square and rectangle, into circular boundaries suitable for the construction of domes. This method shaped the initial inspiration for the patching technique to divide the span of the boundaries using self-supporting elements such as the squinches and pendentives, and finally domes. I have been inspired by the work of my colleague, my great friend, Ahoban Oval, on the topology finding of patterns for structural design to develop this patching design grammar. Here I'm going to present the workflow of the patching design grammar. First, the user will define a boundary. Then they have to design the topology for that given boundary. And they will find, using that topology, a geometry of the bolts. And then they will run the structural analysis, and then they will print. As you can see in this workflow, the patching design grammar is divided by two main parts. It's design grammar and parametric design. The design grammar is for topological exploration, and it's rule-based, and it shapes the skeleton of the design. However, the parametric design is for geometrical exploration, and it's parametric driven, and it's for more detailed design. So we can see that the design grammar will shape the skeleton of the walls, and the parametric design will change the shape and geometry. In order to introduce the patching design grammar, several terms should be defined in advance. First is a layer. Layer or lace is a continuous mortar extruded from the digitally controlled nozzle. The second one is a patch. Patch is a 3D printed domain in which the lace is continuously printed. And the last is a multi-bolt. Multi-bolt is the aggregation of several interconnected patches. As you can see here, we have a multi-bolt with 9 different patches covering a square boundary. Each patch has 4 identical properties. The first one is a rule, the second one is a support type, third one is a support configuration, and last one is a bolt type and position. I'm going to explain each one separately. First is a rule. Rule in patching grammar is in 2 classes. First is the primary rules, which are directly inspired by the ancient bolting techniques with no formworks. So in primary rules, we have bolt, squinch, pendentive, Nubian bolts, and dome. And hybrid rules are the rules that share the characteristics of 2 or several primary rules at the same time, such as the squinch pendentive and hybrid domes. The support type in the patching design grammar are twofold. First is the ground support, and second is the patch support. The first example shows the ground support, where a squinch is supported totally by ground, and the red part shows the ground support. The second one is an example of patch support, which is mentioned by the dashed purple color line. As you can see here, there is a pendentive which is supported by two lateral squinches using two patch supports. Here we have one squinch and one squinch pendentive, which are supported together using the patch support. And the last example is the wall, the pitch wall, which is supported by patch support using a wall. The support, regardless of their types, which is ground support or the patch support, they have three different configurations. They can be either line, polyline, or curve, or closed or periodic boundary. The mesh quad topology in the field of patching grammar can be served for two manners. First, for defining the topology of the multi-vaults. Second, in order to define the print direction or print path of each patch. For example, here we have a decagon with the topology of the quad. And as you can see, if we take the strips of this quad, we can define a print direction for this boundary. The poles in the quad meshes are type of singularities that are adjacent to the pseudo quad faces. The poles are in two types, partial pole or full pole. The full pole are the poles that are fully adjacent to the pseudo quad meshes, quad faces, and the partial pole are the poles that are partially adjacent to the pseudo quad faces and partially adjacent to the real quad faces. So here in the example, we have a support of a squinch in which the pole is I think because of this connection. So in which we have the pole outside the configuration, and as you can see, as a consequence, a print direction the parallel to the support of the squinch. The second example is a squinch in which we have a pole position on the boundary, and as a consequence, we have a print direction parallel to the arch of the squinch as it's highlighted in the green part. The last part is about the rule titling. Each rule is defined by the title using four letters. The first letter stands as a rule type, which is R. The second one is S, which stands as a support type. Third one is the C, stands as a support configuration, and fourth one is the P, stands as a pole. So please, since I don't have enough time to explain everything, please refer to the manuscript for definition of the subscript and further information. Here, I'm going to present the catalog of the rules in the patching design grammar. The first list is a list of the primary rules in the patching design grammar. As you can see, first we have a wall. The wall can be defined in three different topologies. Then we have a squinches. Then we have a pendentive, Nubian walls, done. And this catalog is the catalog of the hybrid rules in the patching design grammar. First, we have a squinch pendentive, which shares the characteristics of squinch and pendentive at the same time. Then we have, now, since I don't have enough time to explain everything, I will explain one squinch pendentive, how it works. Here, as you can see in the 3D, we have a 2D topology of the squinch in this part. I don't know this. And then in 3D, you can see the purple dashed line is support, which is supported by a previously printed squinch. And then the ground support is theoretically there. So the first layer of the our squinch pendentive can be positioned like this. And this is how it's supported by ground and squinch. The next rule in the hybrid rules in the catalog is a hybrid dumps. So we can see here the configuration of them. Using a patching design grammar, we have two design approaches. The first is the generative design, and second is an analytical design. In the generative design, the user has to define the topology of the multi-vault. However, in the analytical designs, the topology is designed using analytical tools such as the net triangulation. And in this way, the design is fully automated. So the first example is a generative design example in which we have a boundary, then we have a make decomposition of the boundary, making coarse mesh. We densify that mesh, we find the global form, we make we identify the patches based on the topology on the global form, and we tune the geometry of each patch on the global form, and then we define the print parameters. Then we run the FEI analysis. If the analysis is not satisfied for printability, we have three options to modify the geometry. The first one is a minor change, which comes back to the geometry tuning and geometry optimization. The second one is a moderate change, which comes back to the global form finding. And the radical change would be changing the topology of the structure. Then, if the constraint is satisfied, we can print. The other example of the generative design is having here the user has a boundary, and he will define three different topologies for that given boundary. And as you can see, for the results, they have three different multi-volt with different type of patches and number of patches. So in order to explain you how the patches can be printed, I will animate one possible print patch sequence for the second example of the user in this slide. As you can see on the top right, there is a topology of the volt, and numbers indicate the order of the patches that should be printed. So here we have the first patch, second one, third one, fourth, fifth, sixth, seventh, and eighth. The second approach in the patching design grammar is the analytical design approach, in which the topology design is in an automated manner. So here the user will propose a boundary, then they run the Delaunay triangulation analysis on that given boundary. The Delaunay triangulation will give the topology of the multi-volt, and then they have to transform into the coarse mesh and find a global pinnacle form and tune the geometry of each patch on the global form and setting the print parameters. Here is another example of applying Delaunay triangulation method on 4 different boundaries. The idea is to show that these analytical tools can even work for complex boundaries. So as a conclusion, first we introduce the literature review and problem statement, research question, and methodology. Then we introduce the patching design grammar. We introduce the identical properties of each patch, and 2 different design approaches using patching design grammar. First is the generative design, and second is analytical design. My contribution in this chapter is highlighted in this rectangle. The third chapter is about material mechanics and structural analysis. The material of this chapter is outcome of my collaboration with a team of material engineers and civil engineers, comprising my supervisor and co-supervisor, and material engineers Anne Minton and Jean-Michel Rera. The outcome of this research will be published in a future article. So for this chapter, the area of contribution is more about geotechnical engineering, material science, and civil engineering. The outline of this chapter, first I'm going to introduce the radiological requirements for 3D printing, then I will state the problem of the research, and then we will talk about evaporation rates from saturated earth material. Then I will talk about undrained cohesion of soils in function of their water quantity, and then we will talk about structural analysis of 3D printed earthen shells. So the first radiological requirement of the 3D printing any material is pumpability. It means that the material has to be fluid enough in order to be pumped and pushed by the feeding pump inside the extrusion nozzle. The second requirement is the workability, meaning that after the material is deposited through the digitally controlled nozzle, it has to be strong enough in order to maintain its shape and does not deform. The third requirement is the buildability, meaning that the material, after the deposition, they have a very limited time in order to increase their strength, in order to maintain the load of the superposing layers. So here, the time is the interval time between printing 2 layers. The last requirement is the stiffness. So here in the left, we can see that we have an infinite Greek extrusion, which I explained earlier. So the material in this regime is stiff enough and it does not deform under the load of the superposing layers. And here we have we don't have a deformation. However, in this example, the material is not stiff enough and it deforms under the load of superposing layer. And we will have a transition from infinite brick extrusion to the free deposition 3D printing regime. The soil mechanics are dependent on the water content and defined as the water mass of water over the mass of solid. So meaning that the water has a very influential effect on the strength of the soils. So the problem statement of this chapter is that the material has a very limited time in order to gain strength, in order to hold the load of the superposing layers. There are numerous models and studies done on the structuration and thixotropy of the concrete material for buildability. However, there are not many models for the earth-based materials. And then there are two different approaches for increasing the mechanical performance of the earth, which are chemical, which by adding additives. However, the additives will increase the footprint of construction. Therefore, our objective is to use physical approach, which is by evaporation, meaning to increase the water quantity of the material during the printing process. Our methodology is to analyze the evaporation rate under heat condition, define the model for the undrained cohesion and Young's modulus of earth, and then we evaluate the time, temperature, and wind speed needed for 3D printing earthen shells. There are two main approaches, as I previously explained, for increasing the mechanical performance of earth-based materials. First is the chemical approach, such as additive by adding additives such as alginate. The second one is the evaporation technique. We want to use the evaporation technique in this chapter. So in order to apply the evaporation technique in the 3D printing process, we have three different methods. First is by convection. As you can see here, we have a nozzle in which we have a heat gun installed beside, and we heat the layer after it's deposited from the nozzle. The second one is by radiation. So instead of heat gun, we can have a heat lamp. And third one is by conduction, in which we have a hot wire covers the printing nozzle, and it heats the material when it's inside the nozzle, and the evaporation will happen after it's deposited. Our objective is to use the heat by convection. So in order to evaluate the drying mechanism of saturated earth materials, J. Munoz has proposed a formula for evaporation rate of saturated porous media, such as concrete and earth. And as you can see in his formula, the evaporation rate is really dependent on environmental conditions, such as vapor pressure at clay surface, vapor pressure of air, relative humidity, wind speed, temperature, and the vapor pressure at the clay surface can be calculated using this formula. And as you can see, the vapor pressure is really dependent on the temperature, meaning that overall, the evaporation rate is dependent on temperature and wind speed, and is more sensitive to the temperature rather than wind speed. So in order to evaluate the feasibility of this formula on the 3D printing, in order to evaluate the evaporation rate in the 3D printing process under heat condition, we have devised another material experiment, which is called wind tunnel. So we have fabricated this box. It's divided by 3 different channels. In each channel, we put one computer fan in which we can control, regulate the fan speed. In front of each fan, we put one material sample. The proportional size of each sample is corresponding to the proportional size of typical printed materials. Then we put this box inside an oven in order to control the temperature of the environment in which the material is exposed to. So with this setup, we will measure the weight of material before and after putting in the oven and being exposed to the wind speed given by the computer fan in order to evaluate the evaporation rate. So we have 3 different wind speed, different time intervals, and three different temperatures. So using 9 different parameters, we can set 27 different environmental conditions. And for each environmental condition, we put 3 samples. We examine 3 samples. So overall, we have 81 samples in order to evaluate the evaporation rate into 27 different conditions. So here we have a graph of the results, classified by the wind speed and temperature. And as you can see in all 3 results, the evaporation is following a linear process. And if we compare the results of the theory meaning that results from the J- formula and the results from the experiment that we did with the wind tunnel. As you can see, the wind tunnel slightly has a higher evaporation rate. This can be due to the turbulences in the wind speed of the computer fans, or turbulences of the wind temperature inside an oven, or the time interval in which that we exit the material from the oven and measured on the digital scale. But however, there is a good quantitative relation between these two models, and we can consider using the J- formula for evaluating the evaporation rate in the 3D printing process under this condition. There is also a geometrical effect that we can understand from the J- formula. So here we have a relative drying rate formula that we achieved based on the J- formula. And as you can see in this formula, we have a one straight wall. So this is drying rate of a straight wall, straight earthen wall. So if we have a wall with the height h, thickness b, and length l, you can see the relative drying rate is inversely proportional to the thickness of the wall, meaning that the walls that are thinner will have their material mechanical performance increase faster than the thicker wall. So this is a very considerable note, because the geometry can have effect on the material properties. Now that we have a good understanding on the evaporation rate, I'm going to talk about yield criterion of the soils and rocks. Now we know that what is the water quantity of the material with respect to the evaporation rate. Now we can understand the yield criterion of soils and rocks. So the yield criterion of soils and rocks is dependent on their shear strength, and the shear strength is defined by two factors. First is the on-grain cohesion, and second is the friction angle. Here I have an example of one printed earth-based material. As you can see, the brown spots are representing the solid material, and the blue spots are representing the water. As the evaporation continues, the volume of the water will decrease, and making the solid material being more compacted. This decrease in the volume of the water will increase the on-grain cohesion of the material. However, after the evaporation continues, the water will exit the composition of the material and leave behind the void. In this state, the material is not saturated anymore. Our assumption is that all this formula that is presented in this chapter is valid when the material remains saturated. And when the material is not saturated, the evaporation rate will not be linear and may follow a logarithmic behavior. So our question is that does clay remain saturated in the 3D printing process? The answer is that for the specified Calvin clay, in which that we use in this research, if the water quantity stays above 24%, the mixture remains saturated. And there are two scenarios in which the evaporation rate are not linear. The first is that, as I explained, the material is not saturated. And the second is the case of overheating. So if we overheat the material, there might be the occurrence of the cross layer on the outer surface of the material, which will not let the water molecules exit the material composition, and the evaporation rate will not follow the same model. The pediometer test is a standard geotechnical experiment which measures the consolidation of the soil, and it tells us how compactable and compressible our material is. And the first formula used in this test is measures the volume of the voids over the volume of solids. Based on this geotechnical test, we have achieved two models for evaluating on-grain cohesion of the specified Calvin clay and Young modulus of the specified Calvin clay in function of its water quantity. So the summary of contribution of this chapter is that first we defined the drying rate of saturated earth, and we modeled to determine on-grain cohesion of saturated earth in the function of water quantity. We have achieved two models. And now we have ability to predict the plastic failure of the material under the heat condition. Now we have a good understanding of the material evaporation rate and its on-grain cohesion. We can start structural analysis. So here is the classical stress strain graph of the specified Calvin clay. Here we have a spot in which the material reaches its yield strength. Before this part, the material will behave plastically, and after it will behave plastically. There are three different failure modes in the process of 3D printing earthen cantilevers. First is a plastic failure, second is elastic bottling, and third is equipment failure. In order to predict the plastic failure of the material, we have used runtime failure theory, which basically says that the generated stress at each level of printing should not exceed the maximum compression and tensile capacity of the material. In order to predict the elastic failure of the material, of the structure, we have to calculate the bottling capacity. And bottling is independent from the material strength, but it's dependent to the material stiffness. And also, it's highly dependent on the geometry and the boundary condition of the geometry. There is also the effect of the slicing pattern on the structural behavior of the material. So the slicing pattern can influence in the plastic behavior and elastic behavior of the material. In this slide, I will show you how the slicing pattern can govern the plastic behavior of the material during the printing process. So on the left, we can see that we have the slicing pattern will lead to the occurrence of the local bending moment. In the middle one, we have a combination of the shear stress and local bending moments. And at the right, you can see we have only shear stress between the layers. And this slide, I will show you how a slicing pattern will affect the elastic behavior of the material. So here we have one geometry, which is sliced by three different patterns. So at each level of the slicing, we have calculated the bottling factor of the geometry. And as you can see, at the third one, we had at the ending part of the slicing, we had the higher bottling capacity, showing that for this scenario, the third pattern is the better candidate. So as a conclusion, first we introduced the rheological requirements for earthen printing, which is comparability, workability, and buildability. Then we state the problem statement and research questions and our methodology. And then we introduced our approaches to increase the mechanical properties of soils. We talk about the drying rate, yield criterion of soils, and a structural analysis. Our contribution in this field and in this chapter is highlighted in this curvy The last chapter is about fabrication strategies. Here is the area of this contribution of this chapter, which is mostly about robotic automation. We have divided fabrication in this chapter by the fabrication setup size from small, medium to large. The first prototyping setup was a small setup in which we have the ABB IRB 1200 as a parent, and we have the 3D doodler as a child, and our material was a wooden strand given by 3D doodler company. So using this setup, we attempt to print multi-volt with 9 patches. So using this setup, we had a very high performance material in which we could achieve very ambitious geometries. However, the dimension of the robot was so limited, and we had a very problem with the kinematics due to the low dimension of the robot. And also, the robot was really sensitive to the environment, temperature, and vibration, and it needed very high calibration. The second prototyping setup is the medium setup, in which we have a large-scale robot, ABB IRB 6620, installed on a track, giving us 7-axis freedom for printing. And as a child, we had the custom-made extruder head, and it's a reservoir vest, meaning that we put the reservoir material inside the extruder, and the material is pushed by a pneumatic jack inside the clay extruder fabricated by West Company. And the first prototype we attempted using this setup is a double-layer screech. So the first attempt, as you see, it was failed due to the insufficient bonding between the layers. However, after we modified the printing regime and the geometry of the structure, we could successfully print a double-layer screech using the space by carbon clay without any fibers. And in this model, we used a layer heating process using only one heat gun. The second prototype that we conducted using a medium scale robot is a prototype of a multi-wall with 3 different patches in order to show the validity of the patching design grammar. So the first one, as you saw, it was the first squinch. The second squinch is identical. And the last patch is a pendentive, which is supported by 2 lateral squinch. The material formulation is the same as the previous one, space by Calhoun with 58% of water quantity, and we use only 1 heat gun in order to heat the layers. However, after 1 week of the printing, we observed the occurrence of fold joints between the patches due to the shrinkage, which should be investigated to resolve this problem in the future researches. The last prototype is a large-scale prototyping setup. So for this prototyping setup, we had the same robot as a medium scale, ABB IRB 6620. And as a child, we had the extrusion head, concrete extrusion head made by X3 company. And we had also a feeding pump, which is a multi-mix board. And this pump is able to mix and push the material at the same time, giving us infinite access to the material formulation and increase the fabrication speed. So the first prototype that we perform using this setup is a prototype of a U-shaped ball. So, like as medium scale printing setup, we use only 1 heat gun for heating this setup, and the material failed when the structure reaches 20 centimeters, and we had to stop the printing process. The second prototype that we conducted using this setup is a prototype of a squinch on a wooden ball. So we learned the experience from the first prototype in large scale, and now we intensified the heating process. This time, instead of using 1 heat gun, we used 3 heat guns. And for this prototype, we could successfully print in a squinch, double-layer squinch on a wooden ball, which spans more than 1 meter. To compare the 3 different prototyping setups that I presented. So the prototyping setups are compared based on 11 criteria: pumping system power, kinematic flexibility, reachability, calibration sensitivity, layer heating intensity, print speed, print pulse flexibility, print quality, and material performance, and material consistency, and material capacity. So here, the blue one is the small prototyping setup, which means that it has a high material calibration consistency, material performance, and high robot calibration sensitivity. And here there is the evaluation for the medium prototyping, and this one is for the large one. And here is the comparison of 3. So as a conclusion of this research contribution, we have 3 main contributions. First is the development of the patching design grammar for scaffold-free 3D printed shells. Second is analyzing the structural buildup of 3D printed earthen structures using layer heating method. And third is identifying the challenges and the potential of 3 different prototyping setups for 3D printing scaffold-free printed shells. And as like any other research, there are some limitations and shortcomings which should be addressed in the future researches. The first one is analyzing the effect of the printing sequence in patching technique. Second is analyzing the effect of cross-section infill design on the shell structural integrity. And third is the exploration of solutions to eliminate the occurrence of fold joints between patches. And fourth is the integration of a robust FEA method in the patching design grammar workflow. Thank you very much for your attention.